Right, gents. How do we do this one? How would you like someone like to tell me how they'd like me to write this problem out? Put them all in brackets? Yeah. Everything else in brackets? Yeah. X minus x. It's this side subtracted from that side. X minus 2x is minus x. Next bit. Subtract 2x plus 3y minus 4z from x minus 2y plus 5z. Deliberately doing this because this is a type of problem that causes a lot of confusion, a lot of mistakes. So I'm interested in you telling me what you want me to do. And anyone else offering any ideas as well? Yep. We're subtracting, not multiplying, remember. Yep. You've got to subtract this side from that side. 2x minus x is x, and x minus 2x is minus x. So which one is right? Minus x is correct. You think that minus x. So what next in this problem? Minus 2y minus 3y is equal to? And then the next bit is? Which side is 5z? This one, yeah, sorry. Oh yeah, because that's 4z. This is 5, yeah? Plus 5z minus 4z. It's just 1z. Who disagrees with that? Right. Yeah. What you're gone slightly wrong because what it actually is, if we write it out, it is 5z, a positive 5z, minus 4z. You must be aware that the sign goes with the coefficient that comes after it. Yeah? Those two negative signs make a positive, so it becomes 5z plus 4z, making this 9z. Okay? Now, a couple of other ways you could look at this problem and mean us less likely to make a mistake. It's good that you thought about putting both expressions in brackets, because then you're saying it is all of that number calculated, take away all of that number calculated. Yeah, so the idea of putting them in brackets initially is a good one. If we just look at magic pen. We can do that. We just look at that part, and I want the negative number as well, and the negative bit in that as well. Let's just, if we just look at that part, what that is, that negative sign there is meaning it's -1 times all of that. Yeah? So we could multiply out that set of brackets by multiplying everything by -1. So what we'd have if we did that, we're going to do that separately down here. We wouldn't need the brackets in here. We could do -2y plus 5z. -1 times 2 is -2x. -1 times 3 is -3y. And -1 times -4z is +4z. Now collect the like terms. So x minus 2x is -x. -2y minus another 3y is -5y. Plus 5z plus 4z plus 9z. They get more marks lost in exams, in exam questions, because people make mistakes with the plus and minus signs in their numbers than any other thing at all, really. Another way to deal with this problem is to write, where you've got an expression that's got terms like this, we could write it in this way. X minus 2y plus 5z subtract 2x plus 3y minus 4z. And then deal with it column-wise. So the x column, x minus 2x is minus x, minus 2y plus minus 3y is minus 5y, 5z minus 4z is plus 9z. And really it's whatever way you're comfortable with. Yeah. Jake, are you looking a bit baffled or not? Yeah. So that's more common with numbers, to write them out one number underneath the other and subtract the columns. That's how certainly done it when I was at school, right? But not so many people apply it to expressions like this, but you can do. There's no reason why you can't. You need to have all your terms collected, and of course one of these expressions might not have a term in y in it, but that still doesn't make any difference. Just subtracting nothing away. Okay, so just be careful with positive and negative numbers, and be aware that that sign there, that negative sign goes with that 3. That positive sign goes with the 4. That negative sign there goes with the 2. Alright, and put brackets around things if you're unsure, to make sure you do things in the right order. How could we simplify 2p divided by 8pq? Is there a better way we could write that would help us to see what we could do with that? Because that's a bit old school, that division sign. I really aren't expecting to see that in too much of your maths. We don't write division like that as an engineer or mathematician, really. How would we write that? As a fraction, yeah? So tell me what to put. 2p over 8pq. Yeah. What we must remember, something else we must remember, is this line here, we don't write it mathematically, but that line there implies that there are brackets so that it is all of that divided by all of that. And sometimes certain expressions you need to tell your calculator that. Yeah? So although what I would do is get used to using the fraction button on your calculator to do that type of calculation in one go when you've got numbers for P and Q. Yeah? It's worthwhile. Some people like to do the top and the bottom and then divide the numbers, but then you're going to be rounding and create an error. So try and get comfortable with actually using fractions in the fraction button on your calculator. So how can we now simplify that equation? Or simplify it, that's not an equation because it's not an equal sign, it's an expression. Yeah, you can say, are you saying this 2p over 8 pq? Yeah, you can ably write it like that if that's what you want to do. Two over 8, so you can simplify the 2 over 8. Yeah, let's get rid of that. You can write that, there's no reason why you can't. What you're saying is divide top and bottom. What we're saying here is we could divide top and bottom. Let's do one thing at a time at this stage, by 2. So 2p divided by 2 would cancel that out, and that 8 divided by 2 would become 4. So we'd have an expression that looked like this. P over 4 PQ. And then you're going to say, Lewis, divide top and bottom by P. Divide top and bottom by P. So P divided by P is... Sorry? Is it? Is 10 divided by 10 nothing? 1. Be very careful, that's another common mistake. The P completely disappears. No, it doesn't. It becomes 1. So it becomes 1 over 4 Q. The P down the bottom disappears. Well, it becomes 1, and we don't write 1 times Q, we just write Q. Yeah? But be careful about that one, because I've seen that happen so many times as well. And a variable disappears and then suddenly comes back again because the student remembers that it should be there. They recognise the formula. Right? But P divided by P is not nothing, doesn't disappear. Right? What about 2p squared over 8pq? We can do the same thing with the numbers, can't we? Divide through by 2 to get P over 4 PQ. 2p squared, sorry, over 4PQ. And then when we divide through by P, the top becomes P on its own, and the bottom becomes 4Q. Generally, my students don't get those ones wrong. But they get that one wrong up there because they drop the 1 off to get us a fraction. Just be careful. All right? All happy with that? What we got on the next page? A cubed simplify a cubed plus b cubed times b cubed times c times a times b cubed times c cubed. C to the 5, sorry, that last one. How do we deal with that problem? Can't read, can I? Pretty bored, eh? E squared. Yep. Everyone remember what we can do with these? Yeah. Where you got powers with the same base, so we're looking here a cubed, that's the base, and that's the power. Yeah. So we got an a cubed there, and we're going to multiply it by a. How could we write that as a to the power of 1? Because anything to the power of 1 is itself. Yeah, we're going to formalise that in a minute. So what it is a to the 3 times a equals a to the 4. And then we got base b, we got 2 and 3, so as times b to the 2 plus 3 is 5. And then we got c, what's the power on that c there? 1 times c to the 5, so that's c to the 6. Everyone agree with that? And if we wanted to check, we could say a equals 1, b equals 2, c equals 3, and use those numbers in our calculator to do those two expressions, and they should equal the same number. So if you're ever unsure, plug some numbers in. So that's algebra. We're going to do another little bit. We're going to do a little bit on formalise the law of indices that we've just been using anyway. Basic algebra skills, and right at the end, in a little while, you're going to have a go at some more problems from out of the book. I'll put them on the slides, so if you haven't got the book at the moment, you've still got them to have a go at. I'll show you them in a minute. But you wouldn't go too far wrong if you went to chapter 5 basic algebra, and then if you're comfortable with all that, have a look at chapter 6 further algebra skills, which will be needed next year if it's not needed this year. Then you won't go far wrong in terms of doing something outside this class. Okay, you cannot have too much practice at algebra at the moment, because that getting comfortable with that will make you, and getting proficient at algebra will help you with the more complex math topics without doubt. So, laws of indices. When numbers raised to power have the same base, x in the examples, the laws of indices can be used to simplify. So, like I said before, x here is the base, and I is the power, or indice, or index. Yeah, we can only use these laws if the base is the same. Yeah. The first law is for multiplication, and we just now used that. If we've got x to the a times x to the b, we can simplify that to x to the a plus b. So here we've got x to the 6 times x to the 3. We can say that's x to the 6 plus 3 equals x to the 9. So when two numbers with the same base are multiplied, we simplify by adding the powers. So that's the first law, although they don't necessarily come in any particular order, but in textbooks you usually talk about them in the order that I'm going to do. Second law of division, where we've got x to the a divided by x to the b, and remember with division it's important that you deal with them the right way round. The result is x to the a minus b. It's the index of the numerator, sorry, it's the index of the denominator subtracted from the index of the numerator. So here x to the 7 over x to the 4 becomes x to the 7 minus 4 equals x to the 3. So if we have one number divided by another number, we subtract the denominator index from the numerator index. Okay with that so far? Yeah. If we have third law, we have a number of a particular base raised to a power and then through brackets raised to a second power. We multiply the two indices. So we got x to the a here in brackets, and those brackets are raised to the power of b. The answer is x to the a times b. So here x to the 2, all raised to the power 3, is x to the power of 2 times minus 3. Notice how I've applied brackets there. Yeah. The answer is 2 times minus 3 is x to the minus 6. Oh, I've gone back to second law. It should be fourth law roots. X to the power of a divided by b, so fractional indices used to represent roots, square roots, third roots, and so on. So if we have x to the a divided by b, we can write that as the b root of x to the a. So the denominator of the fraction is the level of the root. The numerator is the index of the variable inside the root. So x to the 5 over 2 is equal to 2 as the denominator, so it's just a plain square root. We usually don't write the 2 in there, do we, by convention. If there's no number there, we know it's the square root of x to the power of 5. Now, what we'll really be interested in this law, okay, is going from the root to the indices form, because we're going to need to do that. Certainly quite a lot we're going to need to do that when we do our calculus. We can't do calculus on roots in that form. We need to put them in indices form to do that. So all of this is a two-way thing. We can go one way or the other, and that's particularly relevant to this law. It will be required to turn roots into fractional powers in later topics, i.e. the reverse process to that shown here. Alright, so that one in particular you're going to need to get used to going backwards and forwards. Reciprocals. X to the minus a is equal to 1 over x to the positive a. All a reciprocal is turn a fraction up the other way. So if you apply the reciprocal of a fraction, you effectively spin it up the other way. So the index changes sign as it goes from top to bottom. So how could we write x to the minus 4? We'd write that as 1 over x to the power of 4. Again, later on, we're going to need expressions without fractions in them. So we might want to get something that's down the bottom of here. If we've got this expression, 1 over x to the 4, we need it in that form. So we bring the x to the 4 up the top and change the sign. 1 over x to the 5 is equal to x to the minus 5. And we've already looked at this a bit as well. X to the power of 1 is equal to x. What's that sign as any number to the power of 1 is equal to that number. So a to the 1 is equal to a. Sometimes that's useful though to write it with the index so we can see what we're doing in the steps of our problem. And the sixth law, power of 0, x to the power of 0 is 1. In other words, any number to the power of 0 is equal to 1. So z to the power of 0 is equal to 1. A to the power of 0 is equal to 1. Any variable to the power of 0 is equal to 1. All happy and comfortable with those laws? And the more you use them, the more you'll remember them and not have to look back and find them. Alright? On the next couple of pages of your notes, these are problems extracted from the John Bird book that I pointed you or show you up at the beginning of the session. Okay? There's a page of practice exercises. They're on page 46 of the 7th edition. Okay, the way that book works is, I think if you've got the 7th edition, the answers like this are in the back. And I've extracted this from a copy of the 5th edition where he used to put the answers in brackets. And when I do problems in electrics, I do that as well. Calculate the total resistance for this circuit, and I put the answer that you've got to get in brackets. Those of you that have already been taught with me will be aware of that. So what you're looking at here is do that problem. That's the answer you should get in brackets there. So you've got something to head for. Okay? So there's a page on brackets and factorization, and there's a page of problems on laws of indices. Okay, if you're finding the first few really easy, move on to the later ones, do the hard ones and have a go. Okay, for the rest of the session till 12:30, have a go at some of those questions. I'm here to help. All right, and then have a go between now and next week as well, please.